So in last class we discussed about nucleophilic substitution reactions SN1, SN2, yes Priyal, Sanvi, Urvashi, Amisha, Hitanshi, Nandini, Drumil, Shreya, Vihang, only 9 till now. Drashti, Vranda, Rucha, so in last class we discussed about nucleophilic substitution reactions of haloalkane haloarene compound, that is SN1 and SN2, how they proceed via different mechanism based on the type of haloalkane compound you have. They follow either SN1 or SN2 type of reactions, and then last will even summarize that if you have a tertiary haloalkane compound, they follow SN1. If you have primary haloalkane compound, they follow SN2 type of reaction. Yes, Sanskriti. Now today in this we have to study one topic. I will like to clarify you these terms: inversion, retention, and racemization. Now I have one reactant C, C2H5, X, CH3, and H. So actually this is CH3, C, CH2, CH3, here I have H and here I have X. This is the reactant I have. To this even I can show like this. Now if this is reacting with some nucleophile Y, as this is more electronegative, bond cleavage, heterolytic bond cleavage, at the end of heterolytic bond cleavage, Y gets substituted at the place of X. Now if this follow SN2 type of mechanism, then Y will attack from the opposite side of the X, and as per that the product form is C2H5, Y I have on the side, then CH3. If I have SN2 type of attack, then the product form is like this. Now here if you see, position of X get reversed, and so this product is formed by inversion of configuration. So this process is inversion. But instead Y attach at the same place where we had X, then this reaction is known as that this proceeds via retention of configuration. But if in the same, if this Y attached to this by SN1 mechanism, then what happened? So there is equal chances for formation of A as well as formation of B. So 50% product is A, 50% product is B, and so Here what I am getting is racemic mixture, and this is process known as racemization. So whenever you have optically active compound as a reactant, then in that case there are three different possibilities, that either that reaction may proceed via inversion of configuration or retention of configuration, or there may be formation of racemic mixture. So that is racemization. So during SN1 you have formation of racemic mixture, so this proceed by racemization. During SN2 you have inversion of configuration, right? About this we already discussed in detail. So the configuration of the product is always inverted in case of SN2. So here our nucleophilic substitution reaction get over. Now, as we discussed earlier, that chemical reactions of haloalkane, that is of three different types: nucleophilic substitution reaction, elimination reaction, and reaction with metals. This we have already complete. Now we'll move towards elimination reaction. We'll see what is elimination reaction over here. In general, if I ask you what you mean by elimination reaction, write your answer in chat box. What do you understand by elimination reaction? What do you mean by elimination reaction? Yes, to remove. Two substituents are removed from a molecule, and against to it we have formation of pi bond. Against to it we have formation of pi bond. That is the type of reaction which is known as elimination reaction. So here we'll study elimination reaction in haloalkane compounds. So when we have haloalkane with beta hydrogen atom, when we have haloalkane with beta hydrogen atom, and if you heat that with alcoholic KOH, if you heat that with alcoholic KOH, then here in this case you'll get alkene. You'll get alkene. How? So there is elimination of hydrogen from beta carbon, and even along with this elimination of halogen from alpha carbon, and this result in formation of alkene. Let me see this with one example. Suppose this is the haloalkane molecule. I have CH3 CH2X. So the carbon bearing halogen is known as alpha carbon, and the neighboring carbon is known as beta carbon. So as I discuss here, there is removal of hydrogen from beta carbon and removal of halogen from alpha carbon. Against to it there is formation of double bond. So this is the type of elimination reaction. Along with this, here I have H plus, X minus, and even I have KOH, which is my nucleophile over here. So this nucleophile attract this H plus, and so here there is formation of HB. Here this base OH minus attached with H, and with this there is formation of X minus. So this is what is elimination reaction. Now this is a molecule where you have only single side presence of carbon, so only one side you have beta hydrogen present. Only one side you have beta carbon. But instead of this, suppose I have molecule like CH3, CH2, CH2, CH, Br, CH3. Now this is alpha carbon. Now I have two different type of beta hydrogen. One which is attached to terminal carbon and another one which is attached to middle carbon. This is secondary carbon while this is primary carbon. So hydrogen attached to this is primary hydrogen while this is secondary hydrogen. Now in this case, when there is removal of halogen with removal of hydrogen from beta carbon, two different possibilities are there. Two different possibilities are there. If there is removal of beta hydrogen from third carbon, then product is CH3, CH2, CH, double bond CH, CH3. One removal of bromine from here and removal of hydrogen, beta hydrogen from third carbon. 1, 2, 3, 4 and 5. Then the product form is 1, 2, 3, 4, 5 pent 2 in. Even there is possibility that removal of hydrogen may be from beta carbon, which is terminal carbon, first carbon. So CH3, CH2, CH2, CH, double bond CH2. Now again, if I have to write name, pent 1 in. So there is possibility that there is formation of either pent 2 in or pent 1 in. Which one will form in more quantity? So the one which is more stable will form in higher quantity. We know that rule. The one which is more stable will form in higher quantity. Now apply logic of hyperconjugation and write your answer in comment box that which one is more stable, pent 2 in or pent 1 in. As per concept of hyperconjugation, which one is more stable, pent 2 in or pent 1 in? Write your answer in comment box. Yes, Brunda, correct. Pent 2 in is more stable as per the phenomena of hyperconjugation because of availability of more number of hyperconjugation structures. See here, to this, these 3 plus 2, 5 hydrogens can replace 5 electrons, and so 5 different structures are possible as per hyperconjugation. While in this case, only 2 structures are possible, and as per that rule, pent 2 in is more stable. This is the concept of stability, and from this there is name of scientist Sedzev. He gave us rule that when possibility of more than one alkene formation, the major product form according to Sedzev rule is the preferred product over other is that alkene which has the greater number of alkyl groups attached. This is the rule given by Sedzev. The preferred product is that alkene which has greater number of alkyl groups attached to the doubly bonded carbon atoms, right? So as per this also, if you see pent 2 in here in this case, this is the doubly bonded carbon. Here we have two different carbon. Here in this case they have two different substituents, while in case of pent 1 in I have only one substituent present. So pent 2 in form 81%, while pent 1 in form only 19% in the reaction mixture. So pent 2 in is the major product. This is what is elimination reaction of alkene, haloalkane. Elimination reaction of haloalkane, formation of alkene as a product. Now the last chemical reaction, that is reaction with metal. Reaction with metals. So this haloalkane compounds, they react with metals. So most of the organic chlorides, bromides or iodides, they react with certain metals and give you organometallic compounds. These are the compounds where you have organic carbon chain with one metal element present, which is in this organometallic compound you have bond between carbon and metal. Now if we see important classes of organometallic compound, as I discussed with you while discussing that nucleophilic substitution reactions in general, one compound I had given to you, that is Grignard reagent. About that we'll study here. Grignard reagent is a kind of organometallic compound which is RMgX, where X is halogen, magnesium metal that is attached to alkyl chain. This compound was discovered by Victor Grignard in 1900. Now how we get this compound, which is RMgX? So I have alkyl halide, let I take CH3, CH2Br, bromoethane. When we react bromoethane with magnesium in the presence of dry ether, on reaction this will give us CH3CH2MgBr. This will give us CH3CH2MgBr, ethyl magnesium bromide, which is organometallic compound, and that is known as Grignard reagent. Now this Grignard reagent is very much important for us because of here, if you see, there is covalent bond between carbon and magnesium, and even this covalent bond is a highly polar bond. So here carbon is pulling electrons from highly electropositive magnesium. Magnesium being metal is highly electropositive in nature, so always have tendency to donate electrons. At the same time here carbon is getting chance because of electronegativity is more in comparison to metal, that can pull electron towards itself. So here carbon is pulling electrons from magnesium, and this is the reason Grignard reagent is highly reactive. this is the reason, because of this polarity, Grignard reagent is highly reactive. That act as a proton source like RMgX, if you take, and if you react this with H2O, immediately this bond undergo cleavage. Here also I have H plus OH minus from water. This is plus, this is minus. This negatively charged alkyl chain attack on positively charged proton, give you RH plus this Mg combined with OH and X, because this is plus 2, this is minus 1, this is minus 1. So kind of ionic bond formation is there. So this act as proton source. This act as proton source. What? Which one act as proton source? Like water. If have any proton source like water, then this Grignard reagent react with that and gives you hydrocarbon, corresponding hydrocarbon. So means whichever haloalkane you have to that you are reacting with magnesium, giving you Grignard reagent. When you react that with H2O, giving you hydrocarbon. Even you need to carry out all these reactions in dry conditions, because if you have presence of water, this reaction will go on automatically. And this is the reason whenever we react anything with Grignard reagent, always we carry out reaction in dry condition. So this is the important point. Reactions needs to be carried out in dry condition only with Grignard reagent, because have great tendency to react with water. Under reaction, which you have to study under heading reactions with metals, the first one is Grignard reaction. Second one is Wood's reaction. This is very important from exam point of view. Even you studied this reaction in hydrocarbon chapter standard 11. If you take haloalkane, react this with sodium in the presence of dry ether, then you'll get the alkyl chain of double length, because from here this NaX gets removed and these two alkyl chains, they combine to give you double number of carbon containing alkyl chain. Means if I have chloromethane, then the product formed at the end of this reaction is ethane. Instead, if I have chloroethane, then product is butane. Means if I have one carbon, product is of 2 carbon. If I have 2 carbon containing reactant, product is of 4 carbon containing carbon. So you'll always get double number of carbon containing compound. That's it about chemical reactions of haloalkane. Under this, we studied 3 different types of reaction: nucleophilic substitution reaction, elimination reaction, and reactions with matter. Same way, now we have to study about reactions of haloarene. Reactions of haloarene. Now in reactions of haloarene also we'll study all these 3 types of reaction. Yes, of course, here we have somewhat difference, and this is the reason we study this separately. Nucleophilic substitution, electrophilic substitution instead of elimination, and reaction with metals. Nucleophilic substitution. Now you are very well aware what is nucleophilic substitution. So let me directly start in this case about this nucleophilic substitution reaction. So aryl halides. Now alkyl halides, there is polarity present. Easily you can break that bond, add nucleophile attack on alkyl chain, and you have as a product RNU formation easily. But in case of aryl halides, these are extremely less reactive. These aryl halides, they are extremely less reactive towards nucleophilic substitution reactions than alkyl halides. Why? Why they are less reactive? Polarity is there over here also. But though they are less reactive, let me see reasons. So there is multiple reasons after this. One is resonance. One is resonance effect. Now here, this electron pairs which is present on halogen atom. Now these electron pairs which are present on halogen atom, they are in conjugation. They are in conjugation with what? Pi electrons of the ring. They are attached to benzene ring which is having 3 pi bonds. Now these electron pairs which are present on halogen atom, they are in conjugation with the pi electrons of the ring, and because of this, these undergo resonance structures. Now here, yes Hitanshi, your class is still 110. So CCl bond here, now these undergo resonance. Now due to resonance, what happened? There is double bond character. CCl bond acquires partial double bond character. I hope you remember that those structures where we have resonance structures possible due to donation of lone pair of electron. Which is that effect? Plus R or minus R? Write in comment box. Write in comment box. Plus R. Yes, correct. This is plus R effect. Right? Because of this, here you get double bond character in CCl bond. And this result in double bond character in CCl. Now double bonds are generally difficult to cleave in comparison to single bonds, and this result in less reactivity. So cleavage of ArCl bond becomes difficult in case of haloarenes, which is your this ArCl, right? So here this bond cleavage becomes difficult because of double bond character due to plus R effect, and so they are less reactive in comparison to haloalkane. Here I am not showing those resonance structures, as you all know very well that I have benzene ring like this. This is halogen with 3 lone pairs present, donate 1 pair, these electrons transfer over here. So here on ring I have negative charge, and here on halogen I have partial positive charge. This is one reason after less reactivity of haloalkane compounds. Another reason after this, is difference in hybridization of CX bond. Difference in hybridization of CX bond. Yashvi and Urvashi, tell me what is hybridization of carbon in RX and what is hybridization of carbon in ARX. Yashvi or Bansri, then Urvashi, all these three. I want you to answer. Write your answer in comment box fast. Yashvi, Urvashi, Bansri. Hybridization of carbon in RX and hybridization of carbon in ARX. If you don't know, write don't know. Write in comment box. Urvashi is there. I have only 11 students now. Priyal, Hitanshi, Vrunda, Krish, Sanvi, Anisha, Amisha, Vihang. Urvashi is not there? Okay. So hybridization of carbon in RX, as you all know, is sp3, while in case of ARX that is sp2. Here percentage as character in this case is 25%, while here percentage as character in sp2 hybridization is 33.33%. So here you have less S character, while here you have more S character. So higher is the S character, more electronegativity, more electronegativity, and this held more tightly. This result that this held more tightly, and so CCl bond length in haloalkane, these values you don't have to learn, is 177 picometer, while this CCl bond length in haloarene is 169 picometer. So as you see, in case of haloarene, bond length is less, bond strength is more. Bond length is less, bond strength is more. So this is difficult to break shorter bonds, and hence again they are less reactive. Third reason after less reactivity of haloarene compound is instability of phenyl cation. Is instability of phenyl cation. Now when there is ionization, so phenyl cation is formed. What is phenyl cation? This is phenyl cation. Now this phenyl cation, this form as a result of self-ionization. Now when this is formed, this is not stabilized by resonance. So SN1 mechanism is ruled out. So these are the reasons after less reactivity of haloarenes or aryl halides towards nucleophilic substitution reactions. Though they give few nucleophilic substitution reactions in the presence of some withdrawing groups. Now these withdrawing groups, they withdraw electrons from the benzene ring and resulting in allowing the Cl to relieve easily and other groups to attach at the place of Cl and making this nucleophilic substitution reactions easier. Let me go through those reactions now. So presence of electron withdrawing group at ortho and para position increase reactivity of haloarene. Let me see that by reaction. Suppose if I have chlorobenzene and if I want nucleophilic substitution, means I want to substitute Cl by OH minus. So if I have if I have haloalkane, generally I react with H2O or I react with NaOH. Here, if I want to carry out this reaction, I need to react NaOH with the chlorobenzene at 623 Kelvin temperature under 300 atmospheric pressure and in the presence of any acid. Then this chlorine get replaced by OH. That is formation of phenol from chlorobenzene. Instead, if I have presence of nitro group at the para position, as you know that if there is group present on ortho or para position, this will show effect to the one which is attached over here. Then again here I need to treat that with NaOH, but this reaction instead of 623 Kelvin, this reaction easily carry out at 443 Kelvin temperature without applying any pressure in the presence of acid, and the product is para nitrophenol. Instead, if I have presence of more than one nitro group, that is one, two, three, four, 2,4 dinitro-chlorobenzene, then here even I require less temperature. That reaction is carried out only at 368 Kelvin in the presence of acid to get you substituted product. If you have all the three positions, 2 ortho and para is substituted by nitro group. See here, not only nitro, if you have any other withdrawing group, then also this will result in easy reaction. Reaction becomes easy in the presence of electron withdrawing group, as they are withdrawing electrons from the ring. Two, 4, 6 trinitrophenol. So this is how electron withdrawing group presents, making nucleophilic substitution reactions more easy. making nucleophilic substitution reactions more easy as they themselves are withdrawing electrons from the chlorine, not allowing chlorine to take. So, let me see that which kind of effect they are giving on their presence, and so this reaction becomes easier. So, for that, let me go through resonance structures of or para-nitrochlorobenzene. So this is the electronic arrangement when I have para-nitrochlorobenzene. In the presence of OH minus, this OH minus now attack. Nitro is withdrawing group, so has tendency to withdraw electrons. So this bond electrons move towards that. Here I have N double one O, O minus, nitrogen plus. Here both chlorine and OH minus they attach. Here partial bond formation, partial bond breaking is there. Here I have negative charge. See, here there is resonance possible, this electrons transfer over here. At the same time, this pi electrons they go here. Here you have electron withdrawing group and getting a negative charge, means getting electrons, that carbon is getting electrons. So this is most stable structure. Then this negative charge go here and these electrons transfer here. This is intermediate, which is undergoing resonance, and where during these resonance structures the carbon having electron withdrawing group is getting negative charge. In 11th we discuss about stability of resonance structures. There we discuss that whenever you have some electron withdrawing group and on that group if you are getting negative charge, then that structure becomes the most stable in contrast to other structures which is present over there. So as per this rule, the middle one is most stable. Now this will undergo cleavage finally to form product. So if here now there is complete bond breakage between C and Cl, complete bond formation between C and OH. So this is how this is showing effect. Now here if you see, we are always attaching electron withdrawing group at para position, ortho position, ortho para, but not at meta. Reason you know very well, because always there is electron transfer at ortho and para position, never at meta position. Here nucleophilic substitution reactions in case of haloarene is over. In case of haloarene, nucleophilic substitution reactions are very difficult. Next is electrophilic substitution reactions in haloarene, but as time over, we'll discuss about these reactions in next session in Friday's class. Now I want all of you to remain present. See here now I can see only 8-9 students are present, rest of you I don't know, but I want from next class I want you all to present. Okay, homework I'll share in WhatsApp group.